Mucociliary clearance is an important part of our respiratory defense mechanism. This mucus transport system clears foreign particles and bacteria from the airways. Over the next 20 minutes, we will see, in video recorded by Dr. Stanislav Tatkov, how this important mechanism is affected by temperature and humidity. But let's begin by reviewing where mucus clearance fits into the human respiratory system. Every day we breathe in more than 15,000 liters of air, enough to fill around 1,600 balloons. Even in the most pristine environments, that air is not clean and pure. We inhale thousands of dust, smoke, and virus particles, about 100 bacteria alone every minute. More than 150,000 contaminants each day that, if given free rein, can infect and clog the respiratory system. These foreign particles, viruses and bacteria, are trapped in an extremely sticky mucus layer lining the airways. Mucus carries the trapped material into the larynx in a process known as mucociliary clearance. The physiology of this clearance process isn't completely understood yet. Research continues, but let's take a close look at what we do know. We know that mucus transport to clear foreign particles is driven by motile cilia. Cilia are small tentacle-like structures with a diameter about 1,000 times smaller than a human hair, which beat in an asymmetric rhythm. Cilia protrude from most of the epithelial cells lining the airways, densely carpeting the respiratory tract. This was revealed by scanning electron microscope images. Size is indicated by this scale. The cilia are bathed in a watery fluid. The mucus layer, which traps debris, floats on top of this periciliary fluid, and as the cilia beat synchronously, the mucus layer moves, carrying along trapped particles. Now, the exact mechanism by which the cilia cause the mucus to move remains unclear, and it's the subject of intense research. This particular animation is based on the work of Gaber and Preil. The cilia are shown here in slow motion. In a healthy person, they beat much faster, typically around 15 cycles every second, propelling the mucus about 10 millimeters every minute. Zooming out to a video microscopy recording of live tracheal tissue, you can see the tiny beating cilia as flicker throughout the image, and debris floating on the mucus layer as dark spots moving slowly across the field. Let's move now on to the experimental results, which show, with video microscopy, mucus clearance on live sheep trachea under a variety of temperature and humidity conditions. The impact of reduced temperature and humidity on mucociliary transport is shown very clearly in this experiment, which compares the behavior of two tracheal samples. The first, on the left, is at normal humidity. The second at slightly reduced humidity, 90%, only 10% below normal. Size is indicated by this scale. You will see that when the relative humidity of air flowing over the trachea is below 100% for a long period, the mucus layer will dry out. Of course, this prevents proper mucociliary transport, leaving potentially infectious debris stuck in the airway. For both recordings, the air was supplied at 25 liters per minute and 38 degrees Celsius from the humidifier. For simplicity, unidirectional airflow has been used in all the demonstrations. As we mentioned earlier, heat and water vapor are normally partially recovered during expiration. As the clip starts, the right trachea has been exposed to a constant airflow at lower humidity for 15 minutes. Although you can see tiny beating cilia flickering in the background of both clips at this stage, debris in the mucus of the right clip are stationary. mucus transport is essentially stopped. The dark spots, moving quickly across the left clip now, show debris being cleared by effective mucociliary transport. After only an hour at the lower humidity, the mucus layer at the right has completely dried out. The clip is quite short, so let's play it again. Remember, the right trachea has been exposed to 90% humidity for only 15 minutes. Then after an hour, it has dried out completely. Any debris will remain stuck on the trachea and may lead to infection. In the first experiment, we showed that a constant flow of air, even at 90% humidity, can dry out the mucus layer. This next experiment shows that brief exposure to room air inhibits mucociliary clearance, but demonstrates humidified air can restore the mucociliary mechanism. Here we are monitoring the velocity of debris on the mucous surface as it is pushed along by mucociliary transport. The scale, which is 200 microns long, indicates magnification. This tissue has been exposed to unidirectional airflow at 38 degrees Celsius, 100% relative humidity for some time, so mucus transport is operating normally. Just after recording began, temperature and humidity were reduced to typical room conditions. Transport velocity slows until the debris on the mucus layer stops moving almost completely. Transport velocity is restored when we return to body temperature and humidity. Particles on the surface are moving at about 8 millimeters per minute. Let's rewind and replay the video, but plot the velocity, temperature, and humidity on the graph. Mucus velocity is in yellow, temperature in orange, and humidity in blue. You can see the drop in temperature and humidity quickly causes a drop in transport velocity. Transport velocity is restored when temperature and humidity return to normal.